Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you look for videos explaining topics in college mathematics courses, please consider subscribing because you're in the right spot. Let's get into the current video. I want to take a look at what's called the Hessian of a function. And if you watch the previous videos on the total derivative, I had mentioned that the total derivative of a function, say a function that goes from R2 to R3 or R4 to R5, the total derivative provides what we can kind of think of as like a first derivative of one of those. And as we're going to see as the content here unfolds, the Hessian we can kind of think of as sort of a second derivative type of a thing. But let's go ahead and define what the Hessian of a function is. So for a function f which takes Rn to R, so in other words, ordered pairs to real numbers, or ordered triples to real numbers, ordered quadruples, so on and so forth, to individual real numbers. The Hessian of f or we can also call it the Hessian matrix of f, is the following. HF is going to be this matrix consisting of a bunch of second order partial derivatives. The first row is going to be the second order partial f with respect to the first variable twice. The next element of this row is going to be the second order partial of with respect to x1 and with respect to x2, but with respect to x2 first, all the way down to the second order partial of f with respect to x1 and with respect to xn. Right. Then the second row is going to, or well, let's just go down to here. This is going to be the second order partial, and then this is going to be with respect to the first variable, then the last variable, and then all the way down to the second order partial of f with respect to the last variable, again, twice. So this gigantic matrix consisting of second order partial derivatives is the Hessian of the function f. Now what I want to do is I want to give a sort of a more tractable way to compute the second order partial derivatives and to kind of keep track of where things are, what the first row is, what the second row is, something that's a little bit more computationally friendly than just kind of memorizing the order of this. So first of all, note, all right, so the idea is that the Hessian of a function is the total derivative of the gradient of f. Okay, so the Hessian is the total derivative of the gradient of a function. This gives a much easier way to compute this than think of the left-hand side, because the gradient really easy to compute, and then I've got this list of elements of the corresponding vector, which is the gradient, and then the total derivative. We have a very systematic way of computing that. So let's go ahead and compute an example. So let's say I want to compute the Hessian of the function f of xy is equal to, let's say, x squared e to the 4y. So let's compute the Hessian of this function. What I'm going to do is I'm going to start by computing the gradient, and the gradient is the following vector. First component is the partial derivative with respect to the first variable, in other words 2x e to the 4y, and then the second component of the gradient is the partial derivative with respect to the second variable, meaning I would have 4 x squared e to the 4y. All right, and this is, again, the gradient of the function. Let me go ahead and clean this side up. Okay. Now, when we did the total derivative, remember that so this is, again, the d is total derivative. When we computed the total derivative, we said, okay, the first row is the gradient components of the first function. The second row was the components of the gradient of the second component function. And in that context, we had the unknown function, or not the unknown function, the function we started with, was written as a column. So let's just go ahead and, just to keep it in the same format, let's write it as a column vector here. So 2x e to the 4y, and then 4x squared e to the 4y. Again, just so we can kind of match it up with that previous video. Then the Hessian of the original function, which is the total derivative of the gradient, consists of a matrix where the first row is, I take the, ignore the fact that this is already a gradient, I would take the gradient of this, like the gradient of this first component function, the gradient of the second component function, and then just list the entries. If I take 2x e to the 4y as the function I'm starting with, and I take its gradient, I would get 2e to the 4y, and then I would get 8x e to the 4y. Then I would take the second component function, and its gradient would have components 8x e to the 4y, and then I would have 16x squared e to the 4y. All right? And this would again be the Hessian of the original function that we had started with. Okay? Let's do one more example. F of x, y, z is going to be x squared plus yz plus 4z. Compute the Hessian of this function. All right, solution. Again, this is going to be the key, right? Compute the gradient and then compute the total derivative. Well, the gradient of this, and what I'm going to do is I'm going to write this as a column vector, just so I can kind of match it up with when we did the total derivative. So the column vector, which is the gradient, is going to be 2x, partial with respect to y would be z, partial with respect to z would be y plus 4. All right, that would be the gradient of the original function. Now the Hessian, which is the total derivative of the gradient, is going to be this 3 by 3 matrix. The first row is going to consist of what would the gradient of 2x be? 2, 0, 0. What would the gradient of z be? 0, 0, 1. What would the gradient of y plus 4 be? 0, 1, 4. So this would be the Hessian of the original function. Without realizing it, depending on where you are in your Calc 3 course, you've actually already used something related to the Hessian of a function. The discriminant of a function f which takes, say, Rn to R. So the discriminant of this function is the determinant of its Hessian. Now I say that you've already seen this, I don't know if you have or not, but the idea is if you've gone through your Calc 3 course and you have looked at finding critical points of multivariable functions and then classifying them using sort of a second derivative idea, you've probably seen the expression that looks like this. Right? If you've seen that, then you've actually used this idea before. Because if I look at, so for example, if I look at a function going from R2 to R, so in other words, a function of two variables, like f of xy is x squared plus y squared minus 4x plus 2x, or plus 2y, something like that. So sort of a polynomial function of two variables. That is one function of this form, and its Hessian function, or its Hessian matrix, would consist of, right, it would be second partial with respect to x, and then this would be partial with respect to, say, x and then y, and then this would be fyx, and then this would be fyy. And then the discriminant of this would be its determinant, which would be fxx, fyy minus fxy, fyx. And assuming that the mixed derivatives are continuous, we can use the mixed derivative theorem to interchange yx to be xy, and then this would be fxy squared. Therefore, this would be the expression that you use, and you call it the discriminant. We just kind of seem like, okay, where does that come from? Well, it's nothing more than the determinant of the original function's Hessian. And this tells me that this concept of a Hessian is probably useful, perhaps in other contexts. And I'm going to do 2 follow-up videos to this at least, where I'm going to do some applications using the Hessian of a function. And in one example, or one case, we are going to use the Hessian to find a local quadratic approximation to a multivariable function. And then we are also going to use it to classify critical points of, well, here in Calc 3, you probably went from R2 to R. What if I have 3, 4, 5 variables, right? What if I have more variables than X and Y? How can I then classify its critical points? And again, the Hessian is going to be the key to that. But thank you for watching. Please consider subscribing.